Welcome back. Now that we've learned a little bit about the basics of logic, what the symbols are, how they're joined together, and how we can begin to demonstrate the validity of an argument, we already have enough information to start thinking philosophically about logic with an eye to the thought that logic is a complete system. We're going to go on to say much more about validity, for example, than we've said so far. We're certainly not finished with logic. We're not even finished with propositional or sentential logic. But we do have enough in place to start thinking philosophically. For let me always remind you, this is not only a course on logic, it's a course in philosophy. And the main idea I want to present today in these comments is the idea of logic as a complete system. It's a complete language, but it's also a complete system. It's a complete system in something like the way that Euclid's geometry became a complete system during the Hellenistic era. Before Euclid, of course, mathematicians, geometers, had been able to start with a given statement in geometry and deduce another one. Pretty famously, Pythagoras not only asserted the truth of the Pythagorean theorem, but demonstrated how it could be proved on the basis of other undeniable statements. But what Pythagoras did was nowhere near what Euclid accomplished, because the point of Euclid was to collect as many theorems of geometry as possible together and to show that they all could derive from a very small, comprehensible, restricted set of postulates. Famously, Euclid himself seems to have been dissatisfied with the fifth postulate. He would have liked to derive all the theorems of geometry from 4 postulates alone, but he had to add postulate 5 about the existence of a parallel line, not on a line. For a long time after Euclid, his accomplishment remained people's idea of a complete system. And to some degree, we have an idea of Euclid in mind when we say, for example, that logic, even that propositional logic, the kind we're looking at now, constitutes a complete system. And yet, even despite his accomplishment, Euclid left something out that even in, for example, Plato's fantasy of the completeness of a logical system is not even mentioned, let alone worked out. And that is a codification, a statement within the system of the rules that apply to that system. Not only in Euclid's geometry, but in subsequent geometry, subsequent symbolic logic, even down to Frege himself, there was always a certain amount of appeal to intuitions about what seemed like a correct implication from one statement to the next. A bit of hand waving, if you will. And it was Frege who saw that there was a gap here, a need to supply the logical system with the rules of inference. So that's one of the significant contributions to logic that we owe to Frege. And philosophically, one of the beauties of that achievement is that you can now really think of a formal logical system as a complete system. It's got everything you need. It's got a way of providing the statements. It's got ways of linking the statements together. It's got, above all, it's got ways of showing which statements follow from which others that rely not at all on common sense, logical intuition, or experience, really, but rely entirely on rules of inference that can be codified, formalized, and stated within the system. This idea that I want to comment on today, the idea that logic holds everything, can be looked at from a couple of points of view. One of them is the idea that, and now again, we're going to be talking this whole session about propositional logic, truth functional logic. One of them is the idea that every formula, any formula you can state in propositional logic, and by the way, people sometimes use the expression a well-formed formula. Strictly speaking, that's redundant. If it's a formula, if you're accepting it as a formula, then by definition, it is well-formed. So anything that's a formula in propositional logic that is written according to the rules of propositional logic can be stated in a standard form that's called disjunctive normal form. And disjunctive normal form simply means every formula, no matter what internal grammar it uses, no matter how many parentheses you've got to put together, that is nested, if you've got conditionals, biconditionals, what have you, there is a single standard form that every formula can be translated into. It's a disjunctive normal form, which means it's a set of conjunctions that are in turn linked to one another by disjunction, sometimes with a negation in front of the conjunction. For example, this is a case of, it's a partial disjunctive normal form. You've got A and B and C, or A and not B and C, or not parentheses, A and not B and not C. It's not complete, and I'll say why in a second. You can tell when a disjunctive normal form is complete, but this is the form that it takes. Within parentheses, a conjunction, between parentheses, between the conjunctions, disjunction. Now, there are different ways you can translate any formula into the disjunctive normal form. There's a trivial way once you've got the formula and a truth table. Now look, I purposely did not put any formula up here. Just let this be some formula. And you look down on the truth table, and typically the formula will have a value of true on some lines, false on others. Okay, here's what you do. Because what you want to come up with is a large formula that's true when this thing, whatever it was up here, is true, and false when that is false. So here, for example, it's true. And you look over and you see what the values are of the component propositions, A, B, and C. And you see that in this one example, A is true, B is false, and C is true. So that means that the conjunction A and not B and C is true, right, at those values. Now, on some lines of the truth table, typically, because typically we have a mix of trues and falses, on some lines of the truth table, the formula is determined to be false. Now, what happens there? We look over, and here's a sample. A is false, B is true, and C is false. So we have the negation of A, we have B, and the negation of C. And we say all of that is negated. Right. It's a mechanical procedure. Don't worry. This is strictly speaking a minor part of what we're doing. I'm using it to illustrate a point. But this is a mechanical procedure by which you can take any truth table and translate the formula into this disjunctive normal form. You do this for every line in the truth table, and then you take the disjunction. So in other words, it's true here, or it's true here, or it's true here, and so on. And you've got a standard form. Now, what's the practical value of that? Really pretty close to zero, because once you've got the truth table and you've got a formula, there isn't really much value to grinding out the tiresome disjunctive normal form. Right? Nevertheless, the very fact that a standard universal notation exists for everything in propositional logic strengthens our sense of it as a complete system. Our sense of logic as a complete system is further strengthened by the phenomenon you've all observed here and there already of some connectives translating into other connectives. I already commented on the fact, and we're going to return to it when we look at replacement rules, but I commented on the fact that A horseshoe B, if A then B, is equivalent to, can be replaced by, or translated into, not A or B. You may recall in one of our early classes, one student in explicating a particular problem noted that a negated conjunction actually, a negated disjunction actually behaves like a conjunction. This too is something we're going to get to a few units from now. If you have the disjunction A or B and you negate it, you can translate that into not A and not B. It's one of De Morgan's laws. De Morgan's other law is exactly the opposite for conjunction into disjunction. What these examples ought to show is that if you really had to, you could translate every conjunction into disjunctions, or every disjunction into conjunctions, as long as you had a negation too. All right. So I'll skip the demonstration of these claims, and let me just state the conclusion. We can translate conditionals and biconditionals straightforwardly into disjunctions and negations. And in general, in a systematic way, we could translate all statements in propositional logic to combinations of just disjunction and negation alone, or just conjunction and negation alone. Even more than is the case with the disjunctive normal form, the result can be long and quite cumbersome. But that's not the point. The point is that we can have, if we must, we can work with a simplified grammar of connectives in propositional logic. Now you might ask, that's very nice. You've got it down to disjunction and negation, or conjunction and negation. Do you always need to? Do you always need to have a connective plus negation? Couldn't there be some single connective that all other connectives could translate into? It turns out there are two such possible connectives. They're known by different names, but One of them, the Sheffer stroke, this looks like a stroke. It can be written as an oblique line, a P stroke Q. It is also called NAND, which is a way of saying not and. Now, Henry Sheffer spent most of his career teaching at Harvard in the first half of the 20th century, although I can't help point it out, he also spent 1 year teaching at City College of New York in our own CUNY system. And Sheffer discovered and saw the significance of the Sheffer stroke, the NAND, that has the following definition on the truth table. This is why it means not and. P stroke Q is false when P and Q are both true, and everywhere else it's true. Doesn't that kind of remind you of conjunction? Yeah, but reversed. It's the negation of conjunction. There's a companion to the NAND, not surprisingly, known as the NOR. It goes by a couple of different names. It's been called Quine's dagger. It's been called Peirce's arrow. It was among the people who discovered and explained its use was the philosopher Charles Peirce. He himself, with his penchant for completely unmemorable terminology, called it an amphek, from the Greek word amphekes, double-edged. Okay, you could have told, and this is Peirce, who, when other people started using pragmatism to describe their philosophy that he had coined for his own, renamed his own pragmaticism. So as I say, a fondness for the really forgettable vocabulary. Amphek has to go there. Much better to call it Quine's dagger or Peirce's arrow. The point is, as you can also see, the P amphek Q is the negation of the disjunction. It's false, false, false. It's only true when P and Q are both true. Now, there's nothing about NAND that makes it superior to NOR. I'm just going to make a few remarks about NAND, and whatever I have to say about NAND translates, all things being equal, into NOR. Those are, by the way, they can be shown to be the only two such connectives that are possible. By such connectives, I mean the following. Using either NAND or NOR alone, you can define negation, conjunction, and disjunction. And as you already know, once you've got those, you can define all the other connectives. Even an imaginary connective, you can construct some connective, however Baroque, with its really particular combination of truth values, but there will be some arrangement of the Sheffer stroke, the NAND or the NOR, that gets you the same truth values as this new one you invent. So, for example, Suppose you take P stroke P, right? The P NAND P, the combination of P with itself using the Sheffer stroke. You're going to get a column in the truth table that looks like this, FFTT, which you can see is the negation of the column for P. So P NAND P is the same thing as the negation of P. Now, we saw that this is P NAND Q, FTTT. What happens when you take this and NAND it with itself? Well, you already can see that something NAND itself is the negation of it. So what happens when you negate P NAND Q? What happens when you take P NAND Q NAND, P NAND Q? Well, now that's not peculiar at all. In fact, that's immediately recognized as our old friend conjunction. Without too much trouble, you can translate disjunctions. You can translate the connective or into NAND, and then maybe with a little more fun, remembering how to make a negation and how to make a disjunction, you can create a conditional. Now, up to this point, and with respect to the and, the or, and the if then, we've seen that these connectives seek to capture elementary logical relations that we use every day when speaking natural languages. I've already noted the ways in which they might differ from the relations in ordinary language, how the if then is not quite the same as what we might say about if and then in a natural language. Still, those logical connectives are serving a purpose. They're codifying, they're making precise something that we use in more or less vague everyday ways. Nothing like that can be said for NAND or NOR, okay? Unlike what we discovered in the case of in the case of or, in the case of and. The NAND and the NOR, the Sheffer stroke, or Quine's arrow, Peirce's dagger, have no practical value. But these strokes have the considerable theoretical value of showing just how thorough the logical language can be. It is possible to render every logical relation found in thought between two statements, two true or false statements, into a single vocabulary. So again, it's the philosophical meaning of logic that I have in mind when talking about the Sheffer stroke, more than the practical or the dialectical value of logic, right? We're getting a sense of what logic purports to mean, what it can do. Now, it's tempting whenever we define a new term, a new connective, we learn what rules it operates by. It's tempting to see logic as a game-like activity, right? You want a single one, you want a single connective to do everything, we'll make it the NAND. And here's how you define it, and here's how you translate everything. And then we could also define the rules for reasoning with NAND. Starting next week, for example, we're going to learn the basic rules of inference that apply in every valid argument. So we can see, given any set of premises, how to derive the implications from those premises. But again, as I say, one is tempted to look at this as a fascinating, pleasant game. Now, there's nothing wrong with games. Games actually bring lots of joy to lots of people for many hours of their lives, no question. Does logic have a certain game-like nature? Well, yes, in that the rules of activity can be defined, in that one can be set puzzles and then experience the pleasure of solving the puzzles. All that has a game-like nature to it. And yet there's a tension between this game-like nature of logic and the stated ambition, the purported ambition. The purported ambition that logic has to be a science or a mathematics of truth. Even in mathematics, in the abstract reaches of mathematics, you can find this tension at work. I mean, just to be quite candid about myself, as an undergraduate math student, I do remember one day in abstract algebra, we were talking about commutative groups, that is, groups with a single operation that's defined on them, that has certain properties, and a group can be finite. And I said something that I thought to be an innocuous remark about, well, you can just define it. You can say it's a group, you can say it's a ring, you can say it's a field. You just define it and see what the definition leads to. And my dear professor, Lindstrom, looked as shocked as, I mean, if I had proposed that now would be a good time for me to get up on the table and dance around. When he found words again, he said, well, we're not just creating meaningless abstract entities, groups and rings. They're created in this way because by having relations defined on them in this way, groups and rings and fields mirror other things that exist, like numbers or certain kinds of solid properties. For example, the reason we define them is precisely to capture the properties of other sets of objects and the relations that apply within those sets. So I was very much put in my place. And one can speak this way about logic too. It would be a great loss to logic's understanding of itself if it could exist only as a game in which we define certain terms and, as it were, see what happens. Now, although there are different readings of A.N. Pryor's article about the inference ticket, the question of that really fuels Pryor's argument, and also that fueled responses to his argument, is the question of how we're supposed to understand logic. Now, Pryor invents a connective called tonk, and he gives tonk certain properties that appear in the course of logical derivations. Has two properties in particular. When we get to inference rules in our next session, you'll see that, that Pryor takes a property that conjunction has on the one side, and then a property that disjunction has on the other side. But don't worry about that. Here's what's going on with tonk. And I'll represent tonk with a lowercase t. So we would symbolize it A tonk B. And he says, let's define tonk so that the following two operations hold. That tonk operates in these two ways, in implication, in logical proofs. So we've got a statement A, and tonk is defined so that whenever we have A, we can derive A tonk B for any statement B. Okay, let's call that tonk addition. And then the second rule that applies to tonk is that when we have A tonk B for any A and B, we can derive B alone. All right, we'll call that tonk simplification. So you put these two rules together, and they tell you that whenever you have a statement A, you can derive a statement B. Can you derive it legitimately? Prior says, well, the question has no meaning. We defined tonk so that these two operations can work. So we defined tonk so that for any statement A, we can deduce any statement B. And it's easy to see that you just apply tonk often enough, and pretty soon every statement in the world turns out to follow. And indeed, every statement and the negation of the same statement will follow, so everything is true in the system given tonk. Do they follow? Well, he said they follow from the definition of tonk. Now, if logic is a self-contained game, if it is a set of terms, connectives, and rules, then there could be no objection to introducing a connective like tonk. And what Prior says, that everything can be shown to follow, would certainly be true. Needless to say, that would ruin the whole effect of having logic. I mean, we try to use logic to give us confidence that when we start with certain premises and then logic lets us derive the conclusions from those premises, then we can trust those conclusions. We don't want a freewheeling system in which everything turns out to be true, according to which everything turns out to be true. What Prior is leading to, what he has put his finger on without actually discussing, is the separation between the operations within a system of logic and the truth of conclusions that are shown to be true within that system. Another way of putting it is, validity is a matter of the interpretation of statements. Logical method, proof method, is a grammatical system. You know, given this operation, you can use it in this way, you cannot use it in that way. If logic were only the grammar of the operations, like the rules of inference or the rules of replacement, then it would still have all the game-like delight that it now has, but it would not be about validity. It would not give us confidence that when we showed a proof to be valid, it really was valid, that it really did take us from true premises to true conclusion. Now, what kind of explanatory gap is that? It's interesting that even when the magnificent edifices of late 19th, early 20th century logical system were constructed, the philosophers, mathematicians, logicians who put those systems together had only very general, intuitive ways of talking about that question. How do the rules of our system connect up with the actual validity or invalidity of the argument? Frege at one point, in describing the Grundgesetze, that was his own Grundgesetze der Arithmetik, late 19th century, was his own big logical system that was supposed to show how all the truths of arithmetic followed from logic. And Frege himself says, well, you have to give me a little pinch of salt when we get into the system. That is, we had to trust that there was going to be enough similarity between the logical system and the intuitive idea of validity that it seeks to represent. Whitehead and Russell put out the first volume of their Principia Mathematica in 1910. Principia Mathematica, well, it ended up being 3 volumes, but as I say, the first one came out in 1910. Principia Mathematica sought to go back and correct for certain problems in Frege's system and to develop this really quite complex logical arrangement that ultimately could show that the truths of third grade arithmetic are true. That is, that, for example, 1 + 1 = 2 ultimately can be shown to be true if you begin with a set of logical axioms. Now, right now, I only want to draw attention to the date here. And the date of 1910 matters because volume 1 of Principia Mathematica contains that branch of the Principia system that is truth functional logic, or as we're calling it, sentential logic, propositional logic, the logic of individual propositions. Okay, so that's 1910. It was a full 10 years. And I mean, maybe 10 years doesn't seem like a lot, but when you think about the number of mathematicians who were excited about this logical project, the level of thought that they were bringing to its analysis, it's still astonishing that it took a full 10 years from the publication of volume 1 of Principia Mathematica to the dissertation of Emil Post, to whom we return. Because Post was the first one to state in not just intuitive terms, not just in conversational, everyday, or philosophical terms, but in precisely defined mathematical terms, to state the problem of how a logical system is related to the validity it seeks to represent. I mean, Post not only stated the problem, he answered the problem for propositional logic. But right now, I just want to focus on the fact that his dissertation in 1920 and the publications that followed from it, 100 years ago now, were really the first statements of the problem, and specifically of 2 properties of logical systems, 2 desirable properties of logical systems. Post asked, whether the truth functional logic in the Principia Mathematica was sound and whether it was complete. Now, he showed, and it was not that hard to show, that it was sound. By sound, we mean this: a logical system is sound if and only if every argument that's proven to be valid using the rules and axioms in that system is in fact valid. Everything you show to be valid in a logical system is in fact valid. Or to put it another way, you can trust what the logical system and its rules tell you about valid arguments. Now, this is, needless to say, a highly desired property of logical systems. In fact, it's not a logical system if it doesn't have this property, right? Because you just can't rely on it. It could be telling you that certain arguments are valid when they're all over the place. So this is what, I hate to say this, A.N. Pryor did not grasp that the metalogical idea of soundness existed in order to deny the possibility of tonk. The problem with tonk is that any connective defined in those terms quickly gets you reasoning that's called valid within the system that's not in fact valid, okay? If you added tonk to your system, you would have an unsound system. Okay, so there is an external check. It's not just about defining certain terms. As I say, Post found this to be, relatively speaking, the easy part of the argument, to show that you could trust as valid any reasoning that your system told you was valid. The deeper question is whether a logical system is complete. A logical system is complete if and only if every valid argument has a proof in the system. If an argument is in fact valid, a proof exists in this logical system to show that the argument is valid. When an argument is right, when a solution is right, the logical system will tell you that it's right. Now, how Post showed that propositional logic is complete gets kind of complicated. He had to define 5 different kinds of formulas and show that when you arrange them in a disjunctive normal form, you know, these connectives were not among the formulas, and so on. It's a pretty long proof, and we don't need to go into it. It has been revisited and redescribed as recently as the late 1980s, early 1990s. There are some articles that offer new versions of Post's insight and of Post's proof. Now, as I said, that if a logical system is not sound, it's really not much good at all. And it's probably beyond repair, because once it starts generating invalid inferences, you don't know what you could fix about it so that it became a reliable guide to validity. By contrast, a logical system might be sound and useful in many contexts and yet not be complete. Sometimes if you define a language and a set of connectives and you discover that it's not complete, well, that can be repaired. You can add an axiom, or you can add a connective, or you can add a rule of inference. As it happens, propositional logic is complete. We're going to get to predicate logic later in the semester, and the simplest form of predicate logic, that is when you have a quantifier and predicates, that too can be shown to be complete. 10 years after Post, Gödel showed that first order logic is complete. Gödel is perhaps better known, however, because for the fact that in the year after that, in 1931, he showed that higher order logic, second order or above logic, which is the logic that the Principia Mathematica ultimately starts to use, is incomplete. That is, there are going to be statements that you know are true that can be stated within second order logic and cannot be proved. And in fact, you might say, well, then why can't we just add them as axioms to the system? Well, because if you add them as an axiom, then you can generate another statement that is true but can't be proved true in the system. If third grade arithmetic is consistent, then second order logic is incomplete. Now, incomplete, we're going to get to a little second order logic. It's a very usable system. The fact that it's incomplete doesn't disqualify it among logical systems the way it would be disqualified if it were unsound. Okay. Nevertheless, Gödel's proof was highly consequential about the ambitions and the possible scope of highly complex logical systems and whether they could show the truth of arithmetic. But right now, we're still back at that first part of the Principia Mathematica, the part of the Principia that contains only truth functional logic, like the logic that we're using so far. And there, Post's proof stands. As Post argued, truth functional logic is both sound and complete. And that's why, or that's the respect in which truth functional logic, despite some game-like properties that it may indeed have, is not a game that when we say we have shown an argument to be valid, that given certain premises, this conclusion follows. We're right. It really is valid. And the converse of that too. If an argument really is valid, there's going to be a way to get from the premises to the conclusion to show that the argument is valid. This is the more profound way in which truth functional logic is a full and complete system. There's the immediately perceptible way that I was talking about at the beginning of today's remarks, the way in which anything can be stated in a standard form using the disjunctive normal form, for example. Everything can then be reduced to a single logical connective, like the Sheffer stroke, the NAND, or Quine's arrow, the NOR. But even there, we can be operating within a domain where logic only knows itself and logic only plays with its own rules. What Post leaves us with is the confidence that the rules of logic actually capture the validity of arguments. Okay, that's why the metalogic is not just another kind of philosophical question we might make up and ask about logic, but it's one that reflects back on logical practice, and I hope energizes us to go on from here, because what we're gonna begin studying after this is validity from a more streamlined point of view. Validity as that is determined using rules of inference and replacement rules. That's the next couple of sessions we're covering. And then alternatively, for example, with indirect proof or using truth trees. We have all that, I'm glad to say, to look forward to.